First of all, thanks to the organizers for inviting me to come here and to talk. It's been a very pleasant stay, and I still have some more days, so that's good. I'm going to talk about some classical objects in differential geometry and projective geometry. My point of view is really projective geometry, but a lot of these things were studied, first of all, in the real affine setting. So I'll get back to also some real aspects of this theory. I'm going to digress first. So Erasmus Darwin, I mentioned him, we're very close to Darwin College. Darwin College was a gift from the Darwin family, not from Erasmus, he never stayed in Cambridge, nor from Charles Darwin, his grandson, who's even more famous. He studied in Cambridge, but he didn't live here. But Erasmus Darwin was a physician and a poet, and also a man with progressive ideas about science, society, for example, botany. He wrote about the evolution of plants, inspired by Linné, the Swedish botanist who classified plants. And he wrote this poem, The Loves of the Plants, inspired by Linné, but it was about the evolution of plants, about reproduction, and about sexuality of plants. And this was not, because he had these liberal ideas, he was also for the French Revolution. Then in France, mathematics and science and technology became very important, and the introduction of the meter, for example. And all of these sort of new ideas were not taken up well by the conservatives in England at the time. So, for example, George Canning, who later became a prime minister, he wrote a parody of The Love of the Plants called The Love of the Triangles. So this was sort of an anti-mathematical text with a lot of hints to Darwin. And he talked about, he mentioned doesn't this work? Can you see any point? Yes. You can, I can't. Where is it?
Yeah, I do.
What?
It was on for a moment.
It was on for a moment. Maybe the battery is low.
There's a physical pointer right behind you.
Right?
Oh, yeah. Well, maybe. So he mentioned some curves, kissoids, conchoids, pendules, cycloids, and he said that the kissoid is particularly important for poetry. And what is the kissoid? It's a curve describing the leaves of the ivy. And it's therefore peculiarly adapted to poetry. And these footnotes were also a parody of Erasmus Darwin's footnotes. So we'll get back to these curves shortly, but let's first get back to mathematics. Yes?
Do you think that a politician knew these words?
Yeah. I mean, you know. Of course. These were standard curves, right? Huygens goes back the cycloid. I mean, yeah. for people of a certain, education, these things were known. Anyway, so let's get back to the real subject of my talk. So we'll talk about envelopes of families of linear spaces. So I start with the projective variety in dimension R. I take a locally free sheaf or a vector bundle on X of rank n minus R plus 1. And then I look at the corresponding projective bundle. The fibers are linear spaces of dimension n minus R. And we can look at the family we get by taking PF sits inside X plus Pn, and then we project on the second factor. So I get an n-dimensional variety P of F, which is this fiber bundle, mapping surjectively to projective space of the same dimension. And I should say we can take envelopes of families of other varieties, but here I will only consider linear spaces. So the envelope of this family, by definition, is the branch locus of this map. So it's where the map, it's the image of the ramification points of that map. For example, consider a curve in the plane, which is the most natural family of lines you can imagine. That's the family of tangent lines. Okay, so what's the envelope of the family of tangent lines? That's where two tangents come together, so that's just the curve itself. Not very interesting, right? But instead of taking the family of tangents, if we are in a Euclidean plane, each tangent will have a normal. And so we can, instead of looking at the tangents, we can look at the family of normal lines. And then we can take the envelope of that family, and that is what is called the evolute of the curve. We'll get back to this in a while. And these notions are not new. Already Apollonius considered conics. So in his treatise on conic sections, book 5, he actually constructed and studied normals to conics. And he says that his predecessors and contemporaries only superficially touched upon this investigation, that he means of normals, of the shortest lines. So if you have a curve, and you look at the point, and you want to find the shortest line to the curve, of course what you do is you take the normal. So here is the tangent, and here is the normal. So this is what he did. And he says the others only studied straight lines that touch the sections. Otherwise, they studied only the tangents, not the normals. And he found the normals more interesting, and he was able to compute the number of normals through a given point if you have given a conic. And this is what is, you take a point and you look how many normals to the curve pass through that point. And this is what many people now call the Euclidean distance degree. And the envelope, the points where two normals fall together, that's precisely the evolute. So here is the classical example of an ellipse and its evolute. So the blue ellipse has a 4-cuspidal evolute, and the cusps of the evolute are the critical points of the curvature function. So you see you have maximal curvature here and here, minimal curvature here and here, and these points of the evolutes are actually the centers of the circles that approach the curve best, so the centers of curvature is what they're called. And we see that there are, when we talk about vertices of a curve, we do not talk about the cusps of the evolute, which look like vertices, but we talk about the points, corresponding points on the curve. So those are, the vertices are actually points on the curve, not on the evolute. So you see that this conic has 4 vertices, and if you know about the 4-vertex theorem, this is what it is about. And here back to the chisoid. This is the chisoid of Diocles. It's not so interesting as a curve. It's a curve with 1 cusp, but it has an evolute. And here you see the curve is singular, but the evolute is not singular. Okay, so if we want now to consider family of normal spaces to a variety, we need to have a notion of perpendicularity. And this is not, I should probably get them here. Maybe. So if we have a projective space, we choose a hyperplane at infinity, and then we choose a quadric in this space, and we're going to make a perpendicularity in this projective space depending on the choice of the hyperplane at infinity and the quadric. So the quadric could be, in this case it's just could be 2 points. And now what I do is I take a linear space L in the projective space. I intersect with the plane at infinity. So I get a space here of dimension. If L has dimension R, then this intersection will have dimension R minus 1. I take its perpendicular space inside here, where it's polar space. You can take the polar space with respect to, the quadric. And then, now, what is perpendicularity by definition in this setup? I pick a point, and then I take the space spanned by P and the polar of this intersection. And then I claim that this is my perpendicular line. And now you can say that, but this means that all points on this line will have the same perpendicular thing. I mean, we'll pass, if I have here, then this is also perpendicular. That's okay, because you have a line, and all lines that are perpendicular are parallel to the given line. And parallel means that they meet in the same point at infinity. So this is a sort of notion, and this is just a way of saying it here. So example, you can go back to that picture. In the plane, you take Q equal to 2 points. In this case, these 2 points are the circular points. The points 1, I0 and 1 minus I0. The circular points play a big role back in old geometry. And if you do this, you see that you get precisely the usual Euclidean geometry in R2, if you restrict to the real affine plane. So now we can define the Euclidean normal bundle. And I do this by the construction I had over there. But for my linear space, I now take the tangent space to my variety at the point. And then I do my construction. And I find a space NP, which is of dimension n minus r, and which is perpendicular to the tangent space. And I can make these normal spaces into a bundle or into a projective fiber bundle. And I need to know what is this Euclidean, what is this normal bundle? Because eventually I want to apply, I want to find numerative formulas, and so I need to know what these bundles are. I cannot just say, well, you just put them together. You need to know. And I will not go into details with this. Those who know, know, and those who don't know will not get very much illuminated, maybe. P1x of 1 is, should I say, Grothendieck's principal part bundle, order 1 of the sheaf of x of 1. So the hyperplane sheaf induced on x. It means that if you projectivize P1x1, you actually get the projective tangent space. That's the main idea. But anyway, you can, the whole point is that you can express this normal bundle. In the case that I write it here, it's under the condition that x is non-singular and that x is in general position with respect to the plane at infinity and with respect to the quadric. Then I get precisely this result. If not, one has to adjust, which is possible to do, and you will include, for example, singularities of the variety or the non-general position of the variety with respect to the plane at infinity and the quadric. So one gets now a map. So this E in general will be generated by n+1 global sections, and so you get the surjective map, and you will be able to use this P of E as the family of normal spaces to the variety. And now you can define the evolute as the envelope of this family of normal spaces. And Now we want to, in the, and I should say with Richard maybe this morning, that applying traditional intersection theory, a la Fulton, McPherson, Kleiman, one can compute, one has the Chern classes, the bundles, etc., and it's possible to compute the formulas, for example, for the degree of the evolute of a plane curve. It has this form, 3d d minus 1, minus 6 times the number of nodes, or the delta invariant, minus 8 times the number of cusps, k0, or appropriately modified if you have nodes and cusps of higher, I mean, if you have singularities of other types. But you can write this in terms of the singularities. So EX is the degree, sorry, E is the evolute, CX is the cuspidal edge of the evolute. So it's the cusp locus of EX, and which will just be the number of cusps, in this case, of the evolute. So we have a curve of degree 3d, d minus 1, etc., and then it has that many cusps, and this MX is just the curve of normals in the dual projective space. So if you have family of lines, in this case, you have the normals. You can think of these normals as points in the dual space, and then it is a curve of some degree, and the degree you can compute is, if the curve is non-singular, it's just d squared. So this is what we call the Euclidean distance degree, actually. So you see, for example, for, yeah, I don't know, you can figure out the examples yourself from this. Now, so it's also a question, how do you use Chern classes or even Thom polynomials that we will get back to find real numbers? I mean, what are the number? How can you do enumerative geometry over the reals? This is hard. It's worse than doing it. I mean, there is a reason the old persons, mathematicians, actually passed to complex numbers, because everything had a solution and everything was nice. So over the reals, things are harder. So in a work with Cordian Riner in Tromsø and Boris Shapiro in Stockholm, we had a pandemic paper, to put it that way, where we studied evolutes and curve of normals for real plane curves. And in particular, we wanted to sort of see how much of the sort of complex things were realized over the reals. As a sort of guiding line, Klein's formula that says that you cannot have more than d minus 2 real inflection points of a plane curve of degree d, whereas the number of complex inflection points, of course, is 3d times d minus 2. So we can look for similar things. And then we define the R degree of a curve, which is the maximal number of real points that the line will intersect a given real curve. And we wanted to find the maximum of these R degrees for the evolute and for the curve of normals, and to compare with what happens in the complex case. And we found some lower bounds for the first, for the degree of the evolute, and we found that for the curve of normals, the thing could actually be equal to d squared, and that's the same as happens in the complex case. So you see that the degree of the evolute in this non-singular case is 3d d minus 1 in the complex case, and we can only prove that it's at least d minus 2. Our guess is maybe it should be d minus 1, so to get the third like in the Klein case, but we don't know. And then we can do the same thing. I already told you what vertices are. There are the cusps of the evolute, and we can again look at the number of real cusps of the evolute. And we found the lower bound, d times 2d minus 3. And for complex curves, it's 2d times 3d minus 5. And again, you see the leading term. In the first, for the real, we have at least 2d squared, whereas in the complex case, the leading term is 6d squared. So again, it's a third, which may or may not have significance. We don't know. A diameter of a curve is a line which is normal at 2 points. So it's what you think. I mean, it's here is one diameter, here is another diameter. So this means that the normal curve of normals will have a double point. And we ask for the number of maximum number of real double points. And we get more complicated formula that we find a lower bound and we have a conjectural upper bound. And for complex nodes, we have an exact formula, of course. And you see again here, actually we have leading terms the same. So is that significant or not? We don't know. And then we can ask for points that are centers of more than one circle of curvature of the given curve. So that means that the evolute actually has a node, double point. And we can ask about the maximal number of double points of the normal curve. And of course, you should then know, why do I say crew nodes? So this is so there are two types of real double points of a plane curve. One where the two branches are real, and one where the point is real, but the branches are not real. Then, of course, you can have complex nodes with nothing real. And again, we have formulas, and see here, we have a bound which is maybe not good because it's 1/9 for the leading term of the thing in the complex case. So, back to the plants. I want to illustrate what we did with Cordian and Boris. So we have the trifolium curve. It has a nice evolute with 1, 2, 3, 4, 5, 6 real cusps. To the right is the curve of normals drawn in appropriate coordinates in the dual projective plane. And you see, it only has double points, only has crew nodes. It doesn't have, you don't see any cusps. And this is typical of the situation. It has a point of multiplicity 4 at infinity, but we don't see that since I only draw the affine plane. Okay, if I add a leaf, I get the 4-leafed clover. It's the quadrifolium. It also has a very nice evolute and a curve of normals, which doesn't really tell us much, but one can study it if one wants. More complicated flower, the ranunculus. The ranunculoid is a curve of degree 12. Has a evolute, which is a smaller ranunculoid, but with the same number of things, and then the curve of normals. Okay, so that's the end of the botany lesson. So now we will get to Thom polynomials. And so now what I will try to show, or at least hopefully, that instead of using now more sort of classical intersection theoretic methods that I've been used to doing, if you try to formulate your problem such that the answer can be obtained by a Thom polynomial, that's a good thing. So this we can do in the case of the evolute. So now we have a family of linear, envelopes more generally. So now I just take NEF, like in the very beginning. And we look at the family of linear n minus r spaces. We take its evolute. As I said, that was by definition the singularity locus of the morphism psi from P of f to Pn. And so it's the sigma 1. And so we can find the class if we know the Thom polynomial of sigma 1. And what is the cuspidal locus of this evolute? It is given by the singularities of the map restricted to sigma 1. So we get the sigma 1, 1. and then we can go on. And we can iterate this sort of evolution and go until we reach, say, a curve, or we reach something. I mean, we can reach also points, but we can just iterate and iterate and iterate. And this is done for space curves. I think Uribe Vargas is doing a lot of evolutes of, especially of space curves, but also of surfaces in the real sort of differential geometric setting more. And he does this iteration for space curves in high dimension. So how can we, what do we get? The class of EF. It's a fundamental class. I hope that is okay for, this is what I talk about when I talk about the fundamental class in this context. So the class of EF inside Pn, because I've mapped everything to Pn, so these evolutes and things live inside Pn, is the first Chern class of the morphism C. So it's the C1 of the difference of pullback of the tangent bundle of Pn minus the tangent bundle of Pf. And for the sigma 1, 1, we get C1 squared plus C2. And for sigma 1, 1, 1, we get C1 cubed plus 3 C1 C2 plus 2 C3. And we can go on, because if we look at Richard's webpage, I think we can go quite far. But I don't want to compute further. So in this talk, I will only deal with these three, because I look at curves and surfaces in P3. So I don't need anything of higher codimension than 3. So it's also, I mean, it doesn't give much to go on. But the point, of course, is that if we want to compute the degree here, we have everything we need. How do you compute the degree of the first one? This is the codimension 1 thing in Pn, so you have to multiply by n minus 1 hyperplane section. I mean, you have to take n minus 1 hyperplanes and intersect. And then you get something of dimension 0, which you can pull back to P of f and push down to x in order to compute. And once you do that, the only thing that enters will be the Chern classes of x, or of its tangent bundle. The Chern classes of OX1, that's just the C1 of OX1, which is the hyperplane class on x in the original setting of x in Pn. And then this bundle F, you will get when you push down powers of over 1 for the Pf, you will get expressions actually in the Segre classes of F, but the Segre classes you can translate into Chern classes. So everything can be computed in terms of Chern classes of Tx, OX1, and F. So let's consider space curves. So if we have a curve in 3 space, its evolute is the envelope of the family of its normal planes. This was studied already by Monge for military purposes and also sort of civil purposes, because he was developing ways of building things which would either be high enough so that cannonballs would not reach, or water would not come in, or, I mean, he was quite practical mathematician. And he called the evolute the polar developable. And the reason he called it developable is that the polar surface, in this case, is actually a developable surface. And a developable surface is a surface whose dual surface is a curve. So it means that all tangent spaces are constants along lines, and such a developable surface has a cuspidal edge, and the cuspidal edge is this sigma 1, 1, so it is the cuspidal edge, I said the cuspidal locus of the evolute. Darboux called the polar developable, the polar surface, and there are other names that have been used up over the years. Now, this cuspidal edge is the locus of centers of spherical curvature. I said that for a plane curve, the evolute was the locus of circular curvature, but here we have the spherical curvature. And the osculating planes to the space evolute, one can show, are the normal planes to x. One can read differential geometry in Blaschke and Leichtweiss, for example. And one can show that the evolute is, this is what I said, the evolute is the tangent developable of Cx. So they're all connected and connected also in other ways. Now, both Darboux and Monge and Clairaut and other people actually considered this as real curves in affine space. I mean, there was no projective space nor complex numbers, as far as I know, for Monge and Darboux. It was sort of differential geometry in real space. But Salmon, and this is old. I mean, he did projective geometry. So he considered both projective plane curves, projective space curves, and he considered surfaces in P3. And he found formulas for the degrees of their evolutes in very clever ways. Had nothing to do with Thom polynomials, nor Chern classes, nor anything. He was basically thinking in how he could do things, and amazingly ability to find things. And I mean, his formulas work. That's the even more amazing thing. Anyway, so what can we do for space curves? If we have a curve of degree d, genus G, with K0 cusps, we can evaluate the Thom polynomials in the way I said. When x is a curve, it's easy, because when you push things down to x, it's just a matter of dealing with first Chern classes. So it's not, I mean, the formulas are small and it's possible to do easily. And you get formulas like this. For example, what is the easiest curve in space? It's a twisted cubic. So then d is 3, g is 0, k0 is 0. So for d equals 3, the degree of the evolute of the twisted cubic is 12. The degree of the cuspidal edge of the evolute is 15. And the degree of the number of cusps of the cuspidal edge of the evolute is 16. So they're rather high numbers for a very simple curve like the twisted cubic. Now, Salmon did this in his way, and he found that the degree of the evolute is equal to 3d plus d star, where d star is the class of x. And the class of x, the class of a space curve, is the number of osculating planes to the curve that pass through a given point. So it's the same as the degree of the strict dual curve, namely the curve in dual projective 3 space, consisting of where the points are the osculating planes of the curve. And I have formulas for d star, so I can plug that in, and in Salmon's formula, and then I get the first formula. So that's okay. Salmon then found the degree of the space evolute to be 5d plus k2, and this number k2 is the number, I mean, he didn't call it k2, I'm sorry, but I do. So k2 is the number of hyperosculating planes to the curve. So it's those number of places where the osculating plane has order of contact 4 instead of 3. There's a finite number of those. And this number I also have a formula for. And when I plug that in, I see that the second formula is in agreement with Salmon. And unfortunately, he did not try to compute the number of cusps of this cuspidal edge. So I have no way of sort of checking my formula against Salmon's formula, which is too bad, because it's always nice when you know the answer. When you compute and you see, yeah, it works. So let's pass to surfaces. And now for simplicity, I do not want to, I mean, I could say that X is not smooth, and I could deal with the singularities because we can adjust the bundles, but let's assume D is smooth, and in P3, and that it has degree D. So it's just given by one equation of degree D. This is sort of simplest case. Now, if you write the Thom polynomials with Chern classes being the difference of these vector bundles, you get rather, I mean, the first one is not so complicated, but of course it gets longer and longer. And I didn't want to write the whole thing because it takes various lines. So, but you see the kind of things you get. And again, you can just intersect with hyperplane sections, then push down to X and see what you get in terms of the degree. And the first one is a very nice formula. Second looks pretty nice too. And they both have the property that when D is 1, which means that you're trying to do the evolute of a plane, you should get 0. And so why the third one does not have D minus 1 as a factor, I do not know. It could be because something I do is wrong. So I don't vouch for the third one. But if I use the Thom polynomial and plug in, this is what I get. But I would have liked to get a different answer, actually. So again, here I can only rely on Salmon for the first formula. What he did was he considered first quadrics in P3, and he actually computed the equation of degree 12 he took a quadric of a given equation, and he computed the equation of its evolute, which is of degree 12. And then afterwards, later, he actually found the formula which is on the first line. So the first one is sort of certified by Salmon, and the two others are not. I believe in the second, I'm not sure about the third. So now I come to what I had hoped to do during the first days here, but which I have not done. But let me tell you the problem. The local study of the geometry of the evolute of a real surface is well known. So this, I mean, you have a surface in P3, and then you have this evolute, which lives also in P3, and when you think of this surface as living in the projective bundle of normals to the surface, you can think, how does it behave with respect to the surface that you start with? And the point is that since the evolute, the points of the evolutes are the centers of spherical curvature for a surface, when you have two principal directions, so you have two curvatures, and these two curvatures will give you two centers of curvature for spheres that are closest to the surface. And so if you have your surface and you have a normal, you have a normal, and then you will have 2 points corresponding to these two curvatures. The 2 points in the real setting, these 2 points could be on the same side of the surface or each on one side. And the point is that sometimes these two curvatures will be the same. So a umbilic point is a point which is locally sphere-like. Its best approximation at the point is a sphere. And so that's when these two come together. And so actually your evolute is a 2-to-1 covering of your original surface with these umbilic points as sort of branch points. And one would like to find the Thom polynomial for these points, right? So if we look in Porteous' book on the intelligence of curves and surfaces, I think it's called. It's a very nice book with very nice drawings. Everything is well explained, except that this is, of course, done in the real differential geometric setting in affine space. So you don't get any sort of projective information out of Porteous' book. But what he does say is that if you take, this is just a local version of the family of normals, if you take this map and you look at its singularities, the umbilic points are the D4 singularities of this map. So then I went happily to Thom polynomials for D4. And, well, yeah, let me just say that these, in the real case, the singularities come in different versions, different types. And Kasarian has one paper where he distinguishes 4 types. Usually they're just distinguished in 2, but he does this alternating sum and gets 4. And he says this shows that a surface always has at least 4 umbilical points, which is, at least if you think of a sort of spherical ellipsoid or something, that's not so hard to see. Anyway, Uribe Vargas has also studied it in a little bit in projective setting, but also only over the reals. Okay, so how can you approach a D4 singularity? This map, since it's a normal, it's not any kind of fibration. It's actually a fibration given by the normal spaces. And as far as I read, it's supposed to be a Lagrangian map. To be continued. And if I read Mikosh, Pragash, Andrei, then there should be a Thom polynomial for this D4 singularity, and this is just the pullback of a Schubert cycle in the Lagrangian Grassmannian. And the Thom polynomial is A1, A2 minus 2A3, according to their paper. And the problem is, which Chern classes should one really take? Because now this should be in a Lagrangian situation and not necessarily in the situation where the other sort of Thom polynomials live, because at least if I plug in the sort of usual Chern classes of the map, see, then what I get out does not seem to fit with what it should be. So there is some problem here. And so my question is, and if anybody knows the answer, please let me know, which bundles are these Chern classes the bundles of? I mean, which bundles are these AIs the Chern classes of? If the setup at all is correct. I mean, that's also another story. And in this case, I actually do know the answer, which is why, otherwise I could have said, okay, I'll just take these Chern classes, I get the formula. It's maybe correct. But I know that since Salmon actually computed this in a completely different way, algebraically, he found 2d times 5d squared minus 14d plus 11. And that's excluding what happens at infinity. So there is a possibility. He first gave a wrong formula in the sense that he included some points in the hyperplane at infinity, but then he corrected it later. So I know what I should get, but I do not get it yet. So we'll see what happens. But this, I mean, I need to understand this Lagrangian thing. I mean, that's my main problem here, I think. Anyway, now let me mention briefly some, since Richard alluded to in his talk this morning, that in the old days, meaning when I was a student, we did what was new at the time. So what was new at the time when I came to MIT to work with Kleiman? What was new was Fulton's intersection theory. It was the first thing I was handed. Read this, read about Chern classes, read about these notes by Fulton, where he was developing, he and Macpherson, and eventually also Kleiman, where they were developing the new intersection theory for singular varieties. That was the big thing. So now one could do everything properly, even for singular varieties. So what I did, for example, was to give a direct proof of Nutter's formula, or it's a Riemann rock, for a surface by considering a generic map of X to P3, meaning that the image of the surface had a double curve, finite number of triple points, finite number of pinch points, and then I would compute each of these three characters in terms of the degree of the surface and the number of singularities. Degree of the double curve, number of triple points, number of pinch points, and see that it matched. So that was a nice little exercise. And then I was invited to Geneva, I think January 79, and started to work with Felice Ronga. And he said, why don't we do this for threefolds? So that was more complicated, but we did essentially similar thing, mapping the threefold to P4 with generic singularities. So there are many more things to take into account. And of course, Ronga was deep into the theory of singularities of mappings and Thom polynomials. So that's much more of the spirit of that paper than the first paper. So it's sort of in between, should I say, the old-fashioned intersection theory and the use of Thom polynomials. But that also worked. So now I did, sort of out of my thesis, I did, for example, number of triple tangent planes of a smooth surface of degree D. And now, I mean, it's a pity Omoto left, but he has shown me his new great paper, or the draft of it, and he recovers this formula with the Thom polynomials. So that's an application of something I have not had the time to see whether this is much easier than what I did. It's certainly different. And similarly, Kleiman and I computed, among other things, the number of plane curves of degree D with 3 nodes passing through 1/2 D, D plus 3, minus 3 points, just to get a finite number. And in this paper by Omoto, he also found this formula using the Thom polynomials. So again, I have to see more carefully how he did it. And then finally, Søren Nekarda, who is also no longer here, but he was here last week. So he has been doing, with Omoto, formulas for generic space curves. And they also recover formulas that I and others did, again from this Thom polynomial point of view. And in his thesis, Nekarda has considered surfaces in 3 and 4 space, and again found formulas, numerical formulas, I think similar again to at least some of what I did, but with this new Thom polynomial approach. So I think this Thom polynomials are good, should be promoted even more. They should be understood, for me, they should be understood in the Lagrangian setting. To understand them in the real setting, I think is even more challenging. But I mean, I'll leave that to the experts, and then I close early, but I'll give you some time for tea break. He forgot his chair.
I was so immersed.
I see. You were not asleep. Yes?
Could you tell us a bit how Salmon proceeded to get this formula? Just for curiosity.
Yeah, I know. He would, I mean, for example, for the umbilic thing, he would actually end up with a curve and then he would intersect this curve with the surface and say that the umbilical points are these intersections, except that we get some other stuff which shouldn't be part, and then he has to subtract, and he subtracts, and he does this and that. I mean, it's all sort of very, very down to earth, but I don't think I can give you a sort of whole very good right now. But it's, yeah, it's really thinking about all kinds of possible, like in the formula where these other numbers appear, this is because he looks at it in special ways. And sometimes he, I mean, this is also a way, sometimes if you want to find the degree of something, you intersect with the plane at infinity, where things are more special and where you can actually see things. So, I mean, but then you may get something which should not be there, and you have to subtract, and it's, yeah. It's pretty amazing, I mean, how we went about and how we sort of landed at the formulas that he did. And he's not the only one. I mean, all the numerative geometry is sort of full of computations that you, I mean, yeah. Yeah.
So the estimate in the real context, is there a general schema behind, or
Is there a
general technique you are using to get these results, or is this ad hoc to the context?
Oh, you mean the inequalities? Yeah, I should have said that maybe, that a lot of it is just based on Brusotti's theorem that you can deform. So we just start with a number of real lines, and then you deform this way or that way, and yeah. So it's very sort of ad hoc, and which is why we're not saying we have sharp inequalities. We're just saying that, yeah. In the case that we had an equality, for example, for the normals, we could actually construct. But most of the time, it's just you take a line arrangement. You take a line arrangement, and then you.
There is an example with this estimate, or you claim this estimate always holds?
No, the estimate is a lower bound. I mean, when I say it's a lower bound, that's it is a lower bound. I'm not saying that we can find something with that bound. Yeah. No, I'm being on purpose a bit vague because we have, yeah. It's very difficult actually to get exact results in the real case, I think. But
you had drawn those nice pictures with like specific examples in the real case. How, for those ones, how close were they? Like, how close were the bound? Like you had these.
Oh, the ones we had?
Yeah.
No, because those are special curves, and we were looking at sort of all curves of given degree, and then those will be non-singular, and
I see.
so yeah. So no, so these are not really. I mean, like the trefoil, you have a curve with a triple point. So it's not sort of a general curve, and it means, yeah, you get things which you would not expect to get for a general curve of that degree.
I see.
Yeah. No, so it's a very, I mean, first you take, for example, I mean, for the R degree, you take maximal number of intersection point of a real line with a curve, and then you maximize this over all curves of a given degree. And so, yeah. So specific examples will not, I mean, the examples that I gave you were more to give you some pretty pictures than to actually illustrate, you know, our results. But it's, yeah, we could compute, I mean, of course, with the help of a computer, equations of all these things. So Cordian is good at that.